Welcome to Developing Graphics Frameworks with Python and OpenGL, Part 31, Parametric Surfaces and Planes. In the previous video, you saw how to use an equation, the equation of a circle in terms of a parameter t, to generate polygons. In this video, we're going to do a three-dimensional analog of that. Again, we're going to use functions, parametric functions, which take two inputs to describe the surface of a three-dimensional shape. The basic idea is that x, y, and z should each be functions of two variables. Unlike a two-dimensional surface, where x and y were functions of one variable, in a three-dimensional surface, or a surface in three-dimensional space, we want everything to be a function of two variables. We'll call these two variables u and v. So on the left here, think of u and v as living in a completely different space. And imagine you had some kind of rectangular region, illustrated by this. These functions are going to take this rectangular region and wrap it around a surface of some three-dimensional shape. So for example, I might have equations which turn this set of points into the set of points on the surface of a sphere, like in the second diagram. Or a different function might turn this set of points into the surface of a cylinder, which we see here. In general, there's a few ways we could write this function. We could write it as three separate functions, f, g, and h, or we could collapse them into one single function, and I'll call that function to create a surface. I'll call that function s. S takes two inputs, u and v, between two bounds, and it gives us three outputs, where each of those outputs is calculated in terms of the two inputs. Right, and that's the idea. So it doesn't seem like we have much to go on yet. In this video, we're really just setting up the framework, and in the videos which follow, we'll talk about how to figure out what good candidates for these functions are. But right now, we're going to start with a class called Parametric Geometry. So let's head over to our development environment, Sublime Text. And within the geometry folder, let's go ahead and right-click and make a new file. And let's save it right away. This is going to be called Parametric Geometry.py. All right, it's a new extension of the geometry class. So let's start out with from geometry.geometry, import geometry. That's all we need to go on. Our class is going to be called Parametric Geometry. It extends the geometry class. Let's define the constructor. All right, so what do we need for parameters here? Well, if we take a look at that slide we saw a second ago, right, we have a u range in this polygon, or in this rectangle, a range of u values, so maybe like a u start and a u end value, and a range of v values. So we'll have a v start and a v end. They'll often be something like 0 to 1 or 0 to 2 pi, depending on what functions we're using. We also need to know how many sample points to take along each one of these axes. So we'll call that the resolution, and we'll use that to get a set of points. And finally, of course, we're going to need this function. And so those are going to be the parameters of a parametric geometry object. So let's start off and say maybe u start, u end, and u resolution. In the next line, just so it fits nicely, v start, v end, and v resolution. And of course, we need whatever the surface function is going to be. I'm going to go ahead and call that s. Right, there's our function. Now let's go ahead and start to generate a set of points. Let's generate set of points on the function. We'll kind of take this in two steps. Let's generate a grid of points, and then let's group them into triangles. Right. To generate that set of points, I'm going to go ahead and calculate the space between 2 points. That's often called delta, whatever your variable is. So delta u is going to be the end value minus the start value divided by whatever the resolution is. And this is the width of our segment, and then we divide it into this many parts. And that tells us how large each part is going to be. Same thing, let's say delta v is v end minus v start divided by v resolution. All right. Next, let's create an array to store all the different positions in. This is not our final position data array. This is an intermediate array to make what follows a little bit more clear. All right, now we're going to do a couple of for loops over all the different possible points. So let's say for u, let's call this u index, in the range of u resolution, I actually want +1, right? Like if I divide a segment into 4 parts, I actually need 5 points to do that. The start, the end, and 3 in the middle. So I actually need a +1 here. That's very important. So let's do a for loop, and this is really going to be a 2-dimensional array. So I'll make an array of v values. And then for v index, let's call it, in the range of v resolution +1. Right, now we'll calculate the values of the u and v point. Right, so begin at your starting point, plus, well, you have some offset, delta v, that's been applied some number of times, which is u index. Right, so u index times delta u. Again, think of this as we start at this value and then each time increment the u index increments and goes up. We're going over by another step of size delta u. Same thing, we'll calculate v. Completely analogous formula, v start plus v index times delta v. And then v array, we're going to append a new point, which we calculate from the surface function applied to u and v. And so we'll do that. We'll get an entire row, or I guess column, since v goes up and down, a column of values of grid points. And then we'll take that and we'll append it to positions. So positions.append this v array. All right, and then by the time that outer for loop finishes, we'll have a full 2-dimensional array of points on our surface. Now we're ready for the second step to kind of group this into vertex data. So let's say create 2 arrays or lists to store vertex data. We'll call them position data, starts out empty. Also do color data. All right. We'll also come up with a set of kind of default vertex colors. Let's see, can really be anything you want. So the first 3, maybe I'll do red, green, and blue. And then the next 3, see, maybe I'll do the complements of those. So we'll do maybe a cyan, 0, 1, 1. We'll do magenta, 1, 0, 1, and we'll do a yellow, 1, 1, 0. All right, I'm just putting that on 2 lines just to make the code a little bit closer. Okay, let's go ahead and group the vertex data, both the positions and the colors, into triangles. All right, so let's say for, now we're thinking in terms of x is like an index, and range of u resolution. And this time we don't need the +1. Right? Before we needed a +1 because we're talking about the different points which separate out each one of those shapes. If the u resolution is 4, then we actually want 4 triangles added in that direction. And then for y index in range v resolution, let's just start adding things in. First, let's start with position data. Just to make this read easier, let's write it like this. PA, position A, from positions. So I'm going to kind of sample with base coordinates at x and y. Right, so I'll start off with this point, x index, y index. Right, now to construct the triangle, I need to go over 1 point in the array and up 1 point in the array. So I'm changing the values of the indices here. So the next point I'll do will be to the right. So positions x index +1, y index. The next point, call that point C. Let's make that the point kind of over and above. So let's say that's positions x index +1 and y index +1. Finally, point D will be positions, the last point is directly above our base point. So that'll be x index and y index +1. If you want these to really line up nicely, I guess you could do +0. And I easily see that we have all the different combinations that we need here. All right, and now we're just going to start adding things into the position data array. So let's see, 2 triangles, PA, PB, PB, PC is our first triangle. And that's kind of the lower side there, followed by the triangle with vertices PA, PC, PD. That's our position data. And next we'll do some color data. This one we'll just do C1, C2, C3, C4, C5, C6. And those will be the colors of our triangles. All right, so at this point, we've populated those 2 arrays with the position data and the color data. So now, we're done with the for loops. Now we just have to add the attributes, and we're just about ready to render. So, self.add attribute. As before, we have a vec3 called vertex position that gets its data from position data. We'll add a second attribute, also a vec3, attached to vertex color. And then we always need to count the vertices. All right. And that's our basic parametric geometry. Now, we can't actually render this yet. Right? This class, think of it as an abstract class. It's meant to be extended, right? Because we actually need to supply some data here. We need to supply a function and the bounds on u and v. So we really want to make sure this works, so let's add a class which extends parametric geometry. Let's create kind of the simplest shape. Again, it's going to be two-dimensional, but existing within a three-dimensional space. Let's make a plane. Right? Slightly different than a rectangle. A plane is a flat surface, but unlike a rectangle, we can subdivide this as many times as we want. Let's go ahead and make a new file. Let's call this one, let's save it right away. And this one will be called, let's see, well, it's a plane, so it would make sense to call it plane geometry dot pi. And that's plane P-L-A-N-E, not airplane or ordinary plane, mathematical plane. So from geometry, for a while we're going to be extending from this class, Parametric Geometry. We're going to import Parametric Geometry. All right, so this class is just plane geometry. And this, again, extends the Parametric Geometry class. So as a first pass, let's give this self. Right, the way each one of these functions is going to work is within the initialization function. Just to make it read nicely, before I call the super function, I want to define my function s of uv. And in each case, it should return some point in three-dimensional space. And so it should return u, v, 0 in this case. That's the parameterization of a plane lying in three-dimensional space. Right, to kind of see what that's going to look like, it's basically going to look like this. Right, it's going to be aligned with the xy axes and perpendicular to the z-axis. All the points will be along z equals 0. And we'll be able to subdivide it into as many points as we want. Right, so there's our function, and we need that to call the super initialization function. And we could do a couple of things. Let's say maybe -1 to 1 and 8 segments. Remember, this is the u start, u end, and u segments. And maybe along the other axis, maybe again we'll go -1 to 1. Maybe in this direction we'll divide it into 5, because why not? And then finally, we need the function, which we've called s. Right, and that will create an interestingly divided square region. The region is going to be square because we have the same width and height between these points. It'll look like it's divided into rectangles, 8 rectangles by 5 rectangles. Let's go ahead and create an application that instantiates a plane geometry. Okay, so I'm going to go back to the root folder and make a new file. Let's save this one as, we're up to test31.py. As before, we do have this template, which makes our life a lot better. Let's copy all the code from the template into test31. And we need to import our new shape from geometry.planegeometry. Import plane geometry. And as usual, what we need to do is change the geometry which is rendering. So now this is a plane geometry. Right, with that change, let's save and build. And if everything's okay, we should see a square. Oh, something's not right. Plane geometry has no attributes. Let's see, self.attributes. Let's see, so this builds off of parametric geometry. Has no attribute called attributes. Let's think about this for a second. All right, the reason it doesn't have an attribute named attributes, right? The problem is it's trying to add something to the attributes dictionary, but the attributes dictionary seems to not exist, The reason it doesn't exist is we forgot at the beginning of this line, right, in the initialization function, we forgot to run the init for the geometry class. So at the top of the file Parametric Geometry, I want to call super.init. Right, and we'll go ahead and save that change right there. Now let's go back to our test file, right, the one where we have a plane geometry. Let's go ahead and try running that again. Come on, rectangle. Hey, there we go. So just like we had hoped, we have something which is the size of a square subdivided into 8 by 5 rectangles. That looks pretty good. Now again, in the interest of building a user-friendly framework, I'd like to actually add some parameters into the plane geometry class. Right? In particular, it'd be nice if the user could specify the width and the height of the plane that they want. We can always give them some default values. So width and height. And also it would be nice for them to choose the resolution. Right? And let's call them width resolution. By default, that's 8, and height resolution. Let's make that 8 as well. So by default, we'll get an 8 by 8 grid. And then down here, right, let's replace these magic constants with, see, if I want the width to be 1, and let's also assume I want this centered at the origin, then I want to go from negative half width to positive half width. So let's do negative width over 2 to width over 2 and width resolution. On the next line, let's say negative height over 2, height over 2, height resolution, and S. Right, this will be a little bit more user-friendly from the application point of view. It'll be a little bit more customizable. Let's save these changes to plane geometry. Let's head back to our test one more time. Let's try it out. Let's try making the width equal to 2, just to see if that works. So save that, and let's give it a final build. So I should get a much wider shape now. Yep, sure enough. It's using the default 8 by 8 subdivisions. It has width 2 and height 1. All right. So congratulations, that's your first parametric geometry. It's not super exciting because we really want to build three-dimensional shapes like spheres and cones, and we'll start learning how to do that in the next video.